Welcome to this lesson on one of the most fascinating paradoxes in nanomedicine, the nanoparticle protein corona identity paradox. This concept challenges everything we thought we knew about how nanoparticles interact with biological systems. So what exactly is this identity paradox? Here's the core idea that turns nanomedicine on its head. The paradox states that a nanoparticle's biological identity is not determined by the properties we carefully engineer into it during synthesis. Instead, the nanoparticle's identity in biological systems is determined by a dynamic shell of proteins that forms spontaneously when the nanoparticle enters a biological fluid like blood. This protein shell is called a protein corona, from the Latin word for crown. It completely changes how cells perceive the nanoparticle. Here's a visualization. On the left, we have a bare nanoparticle with all its carefully designed properties. When it enters blood, proteins immediately absorb onto its surface, creating a corona that gives it a completely new biological identity. You might be asking, why does this protein corona matter so much? Can't we just ignore it? The answer is that the protein corona fundamentally determines how cells interact with the nanoparticle. It affects cellular uptake, where the nanoparticle goes in the body, and even its toxicity. Here's the key insight. Cells don't actually see the nanoparticlets. They only see the outermost layer of proteins in the corona. The nanoparticle's core properties become largely irrelevant. Now let's talk about why this corona is so complex. It's not a static shell, it's incredibly dynamic. The protein corona evolves over time through a process of continuous protein exchange. Proteins bind and unbind constantly. Scientists distinguish between two layers: the hard corona, which consists of tightly bound proteins with long residence times, and the soft corona, which has weakly bound proteins that exchange rapidly. Here we see the two-layer structure. The hard corona proteins have residence times greater than 1 hour and form a stable shell. The soft corona proteins exchange in seconds to minutes and create a dynamic outer layer. Let's look at the key equation that describes protein binding to nanoparticle surfaces. This is based on the Langmuir adsorption model. Theta equals K sub A times the concentration of protein divided by 1 plus K sub A times the concentration of protein. Here theta represents the fractional surface coverage. Theta is the fraction of the nanoparticle surface that's covered by protein. It ranges from 0, meaning no coverage, to 1, meaning complete coverage. K sub A is the association constant. It measures how strongly a particular protein binds to the nanoparticle surface. Higher K sub A means tighter binding. Square brackets P represents the protein concentration in solution, typically measured in milligrams per milliliter or micromolar. Let's work through a concrete numerical example using albumin, which is the most abundant protein in blood plasma. In human blood plasma, the albumin concentration is approximately 40 milligrams per milliliter. That's about 600 micromolar. For albumin binding to gold nanoparticles, a typical association constant is 10 to the 5th per molar, or 10 to the negative 1 per micromolar. Let's calculate. Theta equals 0.1 times 600, divided by 1, plus 0.1 times 600. That's 60 divided by 61, which is approximately 0.98. This calculation shows us that albumin alone would cover about 98% of the nanoparticle surface. This demonstrates albumin's dominance in corona formation. But here's where things get more interesting. There's a phenomenon called the Vroman effect that makes the corona even more dynamic. Here's a question. If albumin dominates initially, does it stay that way forever? The answer is no, and that's the essence of the Vroman effect. Initially, within milliseconds to seconds, high abundance proteins like albumin and immunoglobulins dominate the corona simply because they're present at high concentrations. But over minutes to hours, lower abundance proteins that have higher binding affinity gradually replace the initial proteins. This is called the Vroman effect, named after Leo Vroman, who discovered it. This graph shows the Vroman effect. Albumin coverage starts high, but decreases over time. Meanwhile, proteins like fibrinogen and apolipoproteins, which have higher affinity but lower abundance, gradually increase their presence in the corona. We can describe this dynamic exchange process with a kinetic equation that captures both binding and unbinding. The rate of change of theta sub I, with respect to time equals K on I times the concentration of protein I times 1 minus theta total minus K off I times theta sub I. The first term represents protein adsorption. K on is the adsorption rate constant, and 1 minus theta total represents the fraction of surface that's still available. The second term represents desorption. K off is the desorption rate constant. Proteins can leave the surface and return to solution. The residence time is the inverse of the desorption rate constant. This tells us how long, on average, a protein stays bound to the surface. For hard corona proteins, the residence time is greater than 3600 seconds, which is 1 hour. For soft corona proteins, it's typically less than 60 seconds. Let's estimate the thickness of the protein corona. This is important because it determines the effective size of the nanoparticle. Let's assume we have a monolayer of albumin on a gold nanoparticle. Albumin is roughly ellipsoidal, with dimensions of about 4 nanometers by 4 nanometers by 14 nanometers. If albumin binds with its long axis perpendicular to the surface, the corona thickness would be about 14 nanometers. If it lies flat, the thickness would be only 4 nanometers. The effective diameter equals the core diameter plus 2 times the corona thickness. The factor of 2 accounts for corona on both sides. For example, if we have a 50 nanometer gold nanoparticle and a 10 nanometer thick protein corona, the effective diameter becomes 70 nanometers. 50 plus 2 times 10 equals 70 nanometers. This 40% increase in size can dramatically affect cellular uptake and biodistribution. Now let's discuss the thermodynamics. Why do proteins spontaneously adsorb onto nanoparticles? The answer involves free energy. The change in Gibbs free energy equals the change in enthalpy minus temperature times the change in entropy. For spontaneous adsorption, delta G must be negative. The enthalpy term captures attractive interactions. These include van der Waals forces, electrostatic interactions, and hydrophobic effects between the protein and the nanoparticle surface. The entropy term is more complex. Protein adsorption might decrease conformational entropy as the protein loses flexibility, but it increases entropy by releasing ordered water molecules from both surfaces. Here's an important question. When proteins bind to nanoparticles, do they maintain their native structure, or do they undergo conformational changes? The answer is that proteins often undergo partial unfolding or conformational changes when they bind to nanoparticle surfaces. This is especially true for hard surfaces like metals. These conformational changes can expose hidden epitopes, which are parts of the protein that the immune system can recognize. This can make the nanoparticle immunogenic, even if it wasn't designed to be. This diagram shows the unfolding process. The native protein has a compact structure. Upon adsorption to the nanoparticle, it partially unfolds, exposing regions that were previously buried. These exposed regions can trigger immune responses. So what are the implications of the protein corona for nanoparticle design? This paradox fundamentally changes how we approach nanomedicine. The traditional approach was to carefully design nanoparticle properties like size, charge, and surface chemistry to achieve specific targeting to diseased tissues. But the reality of the protein corona is that these carefully designed properties become masked. The cell receptors interact with corona proteins, not the particle surface. This leads to a new paradigm. Instead of fighting the corona, we should design nanoparticles to recruit a beneficial protein corona that promotes the desired biological behavior. Let me give you a philosophical analogy that captures this paradox. It's similar to the ancient Ship of Theseus paradox. The Ship of Theseus paradox asks, if you replace every single plank of a ship over time, is it still the same ship? Its form remains, but all its materials are different. Similarly, the nanoparticle core remains the same, but its biological identity is completely determined by the ever-changing protein corona. Which is the real identity? Just as the ship's identity is questioned when all its parts are replaced, a nanoparticle's identity is fundamentally altered by the protein corona that replaces its designed surface. The protein corona also has profound implications for personalized medicine. Here's why individual variation matters. Different patients have different plasma protein compositions. This varies with disease state, age, genetics, and diet. This means the same nanoparticle will form different coronas in different patients. The biological identity becomes patient-specific. This helps explain why the same nanomedicine can have variable therapeutic responses in different patients. It's not just the drug, it's the corona that differs. For example, cancer patients often have elevated levels of acute phase proteins and altered lipoproteins. This means a nanoparticle will have a different corona composition in a cancer patient compared to a healthy individual. One strategy to control the corona is the use of stealth coatings. The most common is polyethylene glycol, or PEG. PEG forms a hydrophilic polymer brush on the nanoparticle surface. This brush creates a steric barrier that resists protein adsorption, reducing corona formation. For effective steric stabilization, the PEG chain length L must be greater than its radius of gyration R sub g. This ensures dense brush formation. However, PEG is not perfect. Even pegylated nanoparticles still form a protein corona, just a smaller one. And there's emerging evidence of anti-PEG antibodies in some patients. Let's return to the competition between hard and soft corona. This competition determines the final corona composition. The association constant equals the ratio of K on to K off. Proteins with high K sub A have either fast binding, slow unbinding, or both. Proteins with high association constants dominate the hard corona because they bind strongly and don't easily desorb. Proteins with low association constants form the soft corona. They bind and unbind rapidly, creating a dynamic equilibrium. Here's an exciting application, using the protein corona as a fingerprint for disease detection. Different disease states alter the plasma protein profile. For example, cancer, cardiovascular disease, and Alzheimer's all have characteristic protein signatures. Nanoparticles can capture these disease-specific protein signatures in their corona. By analyzing the corona composition, we might detect diseases. This is a beautiful example of turning a problem into an opportunity. The protein corona, which complicates drug delivery, becomes a tool for diagnosis. For a more complete picture, we need to consider competition among multiple proteins simultaneously. This extended equation includes a summation over all proteins. The available surface is 1 minus the sum of all coverages. The last term represents exchange, where protein I is displaced by protein J. This creates a system of coupled differential equations that's quite complex. Each protein's dynamics depends on all the other proteins present. Numerical solutions of these equations reveal rich temporal dynamics with multiple timescales, explaining the evolving nature of the corona. To experimentally determine binding parameters, scientists use scattered plot analysis. Theta divided by the concentration of protein equals K sub A times 1 minus theta. This is a rearrangement of the Langmuir equation. If we plot theta over concentration on the y-axis versus theta on the x-axis, we get a straight line with slope negative K sub A and intercept K sub A. The slope gives us the association constant. Deviations from linearity indicate cooperative binding or multiple binding sites with different affinities. The protein corona dramatically affects where nanoparticles go in the body, their biodistribution. When immune system proteins, called opsonins, are present in the corona, they mark the nanoparticle for clearance by macrophages in the liver and spleen. Conversely, certain proteins act as disopsonins, helping particles evade immune clearance. Albumin is a key disopsonin. The ratio of opsonins to disopsonins in the corona largely determines whether a nanoparticle reaches its target or gets cleared by the immune system. This diagram illustrates the fate dichotomy. A nanoparticle with high albumin corona has long circulation time. A nanoparticle with high immunoglobulin corona gets rapidly cleared by the immune system. As a nanoparticle circulates through the body, its corona continues to evolve because it encounters different protein environments. In blood plasma, the initial corona forms primarily from abundant plasma proteins like albumin, fibrinogen, and immunoglobulins. When particles extravasate into interstitial fluid, they encounter a different protein environment, with lower total protein concentration but different relative abundances. In the tumor microenvironment, elevated levels of matrix metalloproteinases and other tumor-associated proteins create a unique corona signature. This progressive corona evolution can potentially be exploited for targeting. Particles could be designed to acquire targeting ligands through corona evolution at the disease site. Let's quantify the thermodynamic driving force for corona formation with some numbers. The typical binding energy for protein adsorption to nanoparticles is -20 to -40 kilojoules per mole. The negative sign indicates favorable binding. The relationship is delta G equals -RT times the natural log of K sub A, where R is the gas constant and T is temperature. Rearranging, K sub A equals e to the power of negative delta G over RT. This shows how binding energy relates to the association constant. Let's calculate. For delta G of -30 kilojoules per mole at body temperature 310 Kelvin, which is 37 Celsius, K sub A equals e to the power of 30,000 divided by 8.314 times 310. That's e to the 11.6, which is approximately 10 to the 5th per molar. Here's an important question. Can we design nanoparticles that completely prevent corona formation? Is that even desirable? The answer is that complete prevention is extremely difficult. Even the most sophisticated stealth coatings only reduce corona formation, they don't eliminate it. Furthermore, some corona proteins may actually be beneficial. Albumin corona, for example, can enhance circulation time and reduce toxicity. A better strategy is to control corona composition rather than trying to eliminate it entirely. Design particles to selectively recruit beneficial proteins. The nanoparticle surface charge has a huge impact on which proteins preferentially bind. Positively charged surfaces attract negatively charged proteins through electrostatic interactions. Most plasma proteins are negatively charged at physiological pH of 7.4. Negatively charged surfaces attract the positively charged domains, or patches, on proteins. This can lead to protein orientation effects. The electrostatic energy equals Z1, Z2, E squared divided by 4 pi, epsilon 0, epsilon R times R. Here Z values are the charges, E is the elementary charge, epsilon is the dielectric constant, and R is the separation distance. In physiological conditions with high ionic strength around 150 millimolar, electrostatic interactions are partially screened by ions, reducing their range but not eliminating them. An often overlooked factor is surface curvature. Small nanoparticles have higher curvature, which affects protein binding. High curvature on small nanoparticles reduces the contact area available per protein molecule. This can affect binding affinity. Large proteins with dimensions comparable to the particle size may not conform well to highly curved surfaces, leading to reduced binding. This creates a size-dependent corona composition. 10 nanometer particles and 100 nanometer particles of the same material can have different coronas. The effective curvature radius is approximately the particle radius plus the protein radius. This determines how well proteins can wrap around the surface. Let me summarize the key principles of the protein corona identity paradox. First principle: the biological identity is determined by the protein corona, not by the nanoparticle core properties we engineer. Second principle: the corona is highly dynamic, constantly evolving through protein exchange following the Vroman effect. Third principle: corona composition is patient-specific, varying with disease state and individual protein profiles. Fourth principle: any rational nanoparticle design strategy must explicitly account for corona formation rather than ignoring it. Let me conclude with some future directions and open questions in this field. First question: can we develop computational models that accurately predict corona composition from nanoparticle properties and patient protein profiles? Second question: how exactly does the protein corona affect drug release kinetics from nanocarriers? This is still poorly understood. Third question: can we exploit patient-specific corona formation to develop truly personalized nanomedicines that work differently in different patients? Fourth question: what happens to the protein corona when nanoparticles are internalized into cells? Does it persist or get degraded? The protein corona identity paradox represents a fundamental challenge and opportunity in nanomedicine. It reminds us that biology is complex and adaptive. We can't simply impose our designs on biological systems. Instead, we must work with the system, understanding and harnessing the corona rather than fighting against it. This shift in perspective, from viewing the corona as a problem to seeing it as an integral part of nanoparticle behavior, represents a maturation of the field. The future of nanomedicine depends on embracing this complexity,